Many times while designing heat exchanger as per ASME or the any pressure vessel, we came across requirement of performing the finite element analysis. Vessel can be designed as per Section 8 Division 1 or Division 2 Part 5. But this requirement is now coming very often, and many times design engineer have the question whether what software to be used and how to perform the FEA. So code doesn't speak anything about the software. However, uh, the design engineer need to validate the software, and he should have the training by the software development company to use that software. These are the only basic requirement. Now the second question, how to perform the FEA. So there are many software available in market, Mate, ANSYS, or any other software. But we have the Autodesk Inventor and we have the Nastran as a software available with us. So we tried solving division 2 problem manual like PTB 3 problems using the Autodesk Inventor Nastran. And we compare our result with the PTB results and how to do the analysis, how to create model, how to mesh it using Nastran, and how to evaluate the results and how to compare the results and the reaction forces. These things we will see in today's session. So when I see the PTB 3, there is a problem wherein we need to evaluate the vessel head to meet the requirement of uh, elastic stress analysis criteria, and the material is given SA516 grade 70, which is normalized. Forgings are SA105, and design condition only internal pressure is given as 420 psig at 150 degree Fahrenheit. Corrosion allowance is 1 point. So, and this is the typical configuration of the vessel. So here we can see that uh, this is a typical vessel, and we need to create the 3D model for this vessel. In PTB 3, they have given some guidelines to develop the finite element model. Here they have created 2D element and the axis symmetric model, uh, but we can definitely modify it as per the feasibility in our software. And they have given certain length to be expanded beyond discontinuity, like 5 times square root of RT distance. Uh, so let's, and they have meshed this model. So let's go into the our simulation software, that is Nastran, and see how we have modeled this. So let me go to the Nastran. So here is the Nastran window, and this is the software. So what I have done, I have created the quarter model. So if we see the model in depth, it's quarter model, and in the analysis, I have selected the linear static because we are performing the static analysis. Uh, when we want to see the mesh, so I will just put on the mesh on. I After thorough evaluation, I have, and achieving the mesh convergence. I can explain it in some other session how to achieve the mesh convergence. I have selected the mesh size as zero point 0.3 inches, and we can see there are around 1, 2, 3, 4 elements across the thickness, which is a good quality mesh to proceed. And so we have created same model. This is the forge flange, nozzle extension, the descent, and the shell part. So this is, now let's get back to our presentation. So next part is the material assignment. We have created the 3D model. Now we need to assign the material. So when it comes to the assigning material, we know that material for the forging is SA105, and for the shell and descent or head is SA516 grade 70. The modulus of elasticity value and Poisson's ratio are given. So I have taken this extract from the PTB3. So let's see how we can model this in the Nastran. So in the idealization, I have assigned the material. I have created this material SA516 grade 70, and we can see the density, then the modulus of elasticity, and the Poisson's ratio. These three values I have entered, and I have created the material. For the simplicity, I have assigned same material for the both the things because the properties are very similar. So far we have seen the mesh, we have assigned the material. So these two things we have covered. Now again, we'll go to the next part. This is very interesting part. So we know the pressure, internal pressure is applied as 420 psig on all inside surfaces, and the thrust is calculated, and its value is 982.3 psig. It's applied as a pressure on the raised face area, and there are constraints like they have fixed motion in y direction and rotational motion in z direction. As these constraints are correct when we consider it as a axis symmetric model, but ours is not axis symmetric. We have created quarter model, so we need to modify constraints a little bit. So let's see what constraints we have applied. Constraints. So first one is on this face. So we can see this face is perpendicular to the z-axis. So I have applied symmetry along the z-axis on this face. Another face is this bottom face, which is perpendicular to y-axis. So I have applied symmetry along the y-axis. And the last one, uh, last one is this plane, which is perpendicular to the x-axis. So I have applied the symmetry along the x-axis. So this is slightly different than what we have seen in the 2D element. Now on the pressure part, I have applied the internal pressure of 420 psig on, you can see air load pressure, and it's normal to the surface value is 420 psig. And another thrust pressure which is applied on the raised face of the flange, so that is again pressure, and its value is 490. As loads are applied as pressure, it doesn't make any difference whether we apply it on the element or we apply it on the surface, but it will make difference when we apply the load as force, because pressure is equal to force upon area. So when applying force, we need to be careful about the area on which we are applying the force. So we completed the constraints, we completed the loading, we completed the mesh, and we apply the proper materials. So the pre-processing part of the analysis we have completed. Now we need to right click here, and there is solve in Nastran command. So once I hit that, the software will run. For saving time, I have already run the analysis. So I will just load the results of the analysis. and let's go to the one my stresses. I click on the display. After running the analysis, we can see the displacement, the red dotted lines are the original shape of the component, and this new deformed shape I have deformed it to the scale of 10 times in order to have the clear view, and the stress value is here. So we can see the maximum stress, which is 35,962 psig, and let's see what was the result from the PTB solution, because PTB is run using the different software, but we can see here it's all in Abacus and we are using Nastran. So here is the snap from the PTB. The value is maximum one my stresses is 36890 and ours is 35962. So if we compare both the values, the result, the error, percentage error is about 2.5%, which is accepted because any two software may have some difference in the calculation methodology, as well as the mesh we have selected is different. But since the error is less than 5%, we can say the results are acceptable. Now, very important point in validating the result is the uh, evaluation or calculation of the reaction forces from the software, and calculation comparing it against the applied load. So uh, since this we can check it in any direction, so for this particular assignment I have checked in this y direction. So we are looking at our model from the bottom, and pressure is applied on this projected area. So when so we have the vessel id and the flange or the nozzle id. So this much area or sector of the entire circle having quarter sector, which will be having this much area and 420 psi pressure acting on it. So it will result in a force of 5,52,421 pounds in y direction. At the same time, we have applied the thrust pressure, which is of the value 982.3 psig on the raised face of the flange. The area of sector of raised face is 34.3 square inches, which results in the force of 33,756 pounds. We add these two values, which will give the total force in y direction, and the reaction force which we get from the analysis software, we can see here it's 58,000 5,86,598 pounds. So when we have the percentage error, it is less than uh, 0.1%. So our model is very stable. The actual applied load and reaction forces are matching. So let's check how to see the reaction forces. So I will go on the load subcase and I put reaction. I need to select the entity. So I select the entity over here, and we can see this is the same value we have put into the our actual software. So reaction forces are matching, hence our model is stable, and we can use the result or for the further post processing of the values. So next part is the post processing and evaluation of the result. So we can see these are the areas where the structural discontinuities are there, and we can see the higher values of stresses. And when we go to our software or our analysis, when we look at the output, I have just keep it true scale. Whatever deformation we have introduced 10x times, I have just removed it. So we can see these are the areas where the discontinuities are there, the stresses are high in this area, and the stress representation or the contours are exactly matching with the whatever results the PTB have reported in their book, and those are from the abacus. So now, very interesting part is the stress classification line. There are detailed guidelines provided into the Section 8 Division 2 Part 5 about where to what will be the location of the stress classification line, and how to evaluate the stresses, and how to compare them with the allowable stress, and what will be the value of allowable stress. So I recommend you to go to that section and read. For the simplicity, I have taken this SCL location or the stress classification line location as given in PTB 3 book, and we can see this is the nozzle to flange junction where the discontinuity is there. This is transition of the nozzle. Another one is the shell to nozzle and nozzle to shell junction. So these are the points where the stress classification line has been taken. And there are another stress classification lines taken at crown region, then the tangent line of the descent, shell descent to shell transition, shell to descent transition, and one point is taken away from the discontinuity. So when the uh, s- cell is at discontinuity, whatever the primary stresses we are getting, we are treating them as local stresses and evaluating against the allowable stress criteria of the local stress. And when the HCl is taken away from the discontinuity, we are taking it as a general stresses and evaluating them against the uh, corresponding criteria. So these are the stress classification line, and this is the table which shows the all eight SCL numbers, their location, the respective material allowable for that, and primary membrane, local membrane, and bending stresses. And the evaluation criteria is primary membrane should be less than the allowable. Uh, uh, Local membrane should be less than 1.5 times the allowable, and membrane plus bending shall be less than 1.5 times the allowable. So the evaluation is done, and we have they. So let's understand how to perform the uh, stress classification or the how to put stress classification line and evaluate the stresses. So I am once again going into Nastran, and you can see here the stress linearization entity is there. When we hit on the stress linearization entity, this form will come up, and I have also made mesh visible. We'll take one sample, so I will select this point, and I will put another point over here. Think need to rotate model little bit, then select this point. So we can see the our criteria is one minus stresses, and we have observed the membrane stresses as 7304 psi. Bending is this, and membrane plus bending this. So we can do this exercise for all SCL and report in our readings in the particular format. So let's get back to the presentation once again. So, so here is the thing which we did there. So this is point number one, which represent this, and point number two, which is represented at this location. And we have the PM value. So, and since this is at discontinuity, we are treating it as a local stress. So based on our evaluation and repeating same exercise at different location, so these are the primary stresses, membrane stresses we evaluated against the allowable. And one last stress classification line was away from discontinuity, since we are treating it as a general membrane stress and we evaluating it as a that criteria. So this is our very first exercise, wherein we learn about how to use Nastran to perform the FEA. We solve the PTB problem because PTB is widely accepted as a very authentic resource when it comes to design by analysis method, and they have given very detailed explanation as well as how to perform FEA. The guidelines are there, though they don't talk about the which software to use. So that's the freedom, I guess. And instead of going for very costly software, commercial software, if you have something available with you as a CAD platform and have some FEA capabilities, you can always explore. As per my experience, it is possible in SolidWorks simulation, and it is possible in Nastran. I have shown it using the Nastran for the benefit of all the building engineers who want to learn this fantastic FEA tool, how to use it, and uh, the results are very closely matching. So we created 3D model, we apply the material, we did the meshing, we applied loading, we applied constraint or the boundary condition, we run the analysis, and we did the post processing of the results. So hope you have learned something, and I will have the detailed session about the other analysis in PTB. What are the different types or the materials non-linearity or other aspect, how to see whether mesh is converge or not, how to create a non-linear material model in subsequent sections. So thank you.